Welcome to our presentation on centrifugation, a crucial technique in pharmaceutical sciences. Presented by Professor, Dr. Santosh Kumar Singh from ICFI School of Pharmaceutical Sciences, this session will delve into the objectives, principles, and applications of centrifugation. Centrifugation is one of the most fundamental techniques in pharmaceutical sciences and biochemistry. This powerful separation method enables scientists to isolate components that would otherwise be impossible to separate using conventional filtration techniques. In this presentation, we will explore the core principles, objectives, and diverse applications of centrifugation technology in modern science and industry. Centrifugation is a sophisticated mechanical process that utilizes centrifugal force to separate particles in a mixture based on their physical properties such as size, shape, density, and medium viscosity. This technique is essential in pharmaceutical laboratories, biochemical research, and clinical diagnostics for separating components in liquid samples and suspensions with precision and efficiency. Centrifugation offers significant advantages over traditional filtration methods. It overcomes the limitations of filtration by effectively separating microscopic particles. Enhanced sedimentation accelerates the process, making it invaluable for time-sensitive research and analysis, as it can achieve in minutes what might take hours or days under normal conditions. To fully grasp centrifugation, it's important to understand key definitions. A centrifuge is a device that spins samples at high speed to generate centrifugal force. Radial acceleration is the acceleration directed outward from the axis of rotation, and centrifugal force is the apparent force pushing particles outward during spinning. These principles drive the separation process. Understanding the fundamental principles behind centrifugation is essential for optimizing separation protocols and achieving consistent, reliable results in pharmaceutical and biological research. In this chapter, we will explore the physical laws governing particle sedimentation and the mathematical relationships that determine separation efficiency. The principle of centrifugation is rooted in the natural phenomenon of sedimentation, but with a crucial enhancement. Under normal conditions, particles suspended in liquid gradually settle due to gravity. Centrifugation replaces gravity with centrifugal force, which can be thousands of times stronger, enabling precise separation of components based on their physical properties. Stokes' law provides a formula for the sedimentation velocity of a particle, which is crucial in understanding centrifugation. By replacing gravitational acceleration with the much larger relative centrifugal force, centrifugation dramatically increases sedimentation velocity, making separation possible in minutes rather than days. These principles guide protocol development for specific separation needs. Relative centrifugal force, RCF, measures the actual force exerted on particles during centrifugation, and depends on rotor radius and rotational speed. It's important to note that two rotors operating at identical RPM values can exert dramatically different RCFs if their radii differ. Specifying RCF ensures reproducibility across different centrifuge models. Centrifugation techniques vary based on the separation needs. Differential centrifugation uses sequential spins to separate components by size and density. Density gradient centrifugation employs a medium to separate particles until they reach equilibrium. Isopycnic centrifugation allows particles to migrate to their density equivalent position, creating distinct bands for analysis. Centrifugation serves multiple purposes across scientific disciplines, from basic research to industrial applications. The specific objectives often determine the type of centrifuge, rotor, and protocol selected for a particular application. This chapter outlines the primary and additional goals that make centrifugation an indispensable technique in pharmaceutical sciences and beyond. The primary objectives of centrifugation include separating liquids, removing impurities, isolating crystals, and conducting speed creaming tests. These objectives highlight the versatility of centrifugation in both research and industrial pharmaceutical applications, making it an essential technique for product development and quality control processes. Beyond primary objectives, centrifugation also serves additional goals, such as cellular fractionation, product purification, liquid clarification, and analytical applications. These goals demonstrate centrifugation's role in isolating subcellular components, purifying biological products, and analyzing macromolecular properties, making it a versatile tool in various scientific fields. The applications of centrifugation span virtually every area of pharmaceutical sciences, from basic research to industrial manufacturing. Its versatility and precision make it indispensable for modern scientific endeavors. In this chapter, we will explore the diverse applications across pharmaceutical, biological, industrial, and research domains. In pharmaceutical and biological fields, centrifugation is used for viral purification, clinical diagnostics, protein isolation, and drug development. It enables the separation of blood components for testing, purification of therapeutic proteins, and analysis of drug formulations, demonstrating its critical role in advancing healthcare and research. Centrifugation plays a crucial role in various industrial processes, particularly in the food and beverage industries. It aids in dairy processing, beverage production, and water treatment by separating components efficiently, improving product quality, and ensuring environmental protection through waste reduction. Centrifugation finds applications in everyday life and research. From spin-drying clothes to forensic science and advanced research, it offers insights into macromolecular hydrodynamics and protein-drug interactions. Its versatility extends to household gadgets and scientific laboratories, showcasing its wide-ranging utility. The diversity of centrifugation applications has led to the development of specialized equipment designed for specific separation needs. Understanding the capabilities and limitations of different centrifuge types and rotors is essential for successful experimental design. This chapter explores the major categories of centrifuges and rotors used in pharmaceutical sciences. Centrifuges come in various types, each suited for different applications. Ultracentrifuges reach high speeds for separating subcellular particles, refrigerated centrifuges maintain sample temperature for sensitive samples, and benchtop centrifuges offer compact solutions for routine laboratory tasks. Each type serves a unique purpose in scientific research. Rotors are crucial components of centrifuges, with fixed angle and swinging bucket rotors, serving different purposes. Fixed angle rotors are ideal for pelleting applications, while swinging bucket rotors excel in density gradient separations. Understanding their uses helps optimize centrifugation processes for specific research and industrial applications. In Chapter 6, we delve into short questions and objective-type questions to test your understanding of centrifugation principles and applications. These questions are crafted to reinforce key concepts and prepare you for exams and practical applications in pharmaceutical sciences. Let's start with some short questions. What is a centrifuge? It's a device that separates components by spinning at high speed. The principle of centrifugation involves separating particles based on density differences. Differential centrifugation is a technique for separating particles by size and density. Lastly, RCF differs from RPM as it considers the actual force applied to samples. Now, on to objective-type questions. Centrifugation is based on Stokes' law, and pigments from flower petals are separated by centrifugation. The main purpose of density gradient centrifugation is to purify viruses and ribosomes. The RCF in centrifugation is proportional to the square of RPM. Here's a visual summary of the centrifugation process. Before centrifugation, particles are uniformly suspended. During centrifugation, centrifugal force drives particles outward, and after centrifugation, denser particles form a pellet at the tube bottom while less dense components remain in the supernatant. In conclusion, centrifugation is a powerful technique in pharmaceutical sciences, offering fundamental understanding and potential for future innovation. It enables separations that would be impossible by other means and continues to drive advancements in drug development and diagnostics.